find this. And so when you visualize something like this, you know, sometimes when people are trying to visualize what's happening with resonance, is the double bond moving? So the double bond's here, then it moves here, then it moves here, and then it's back here. So is this just spinning like this, you know, for the double bond? What do you think? You know, as we go from here to here. Or maybe it just jumps randomly, you know. One time it's here, next time it's there, like the electrons. It's jumping random. Well, what we have here is actually, this is, when somebody asks what is the structure of carbonate, this is it. It's not one individual resonance form that's the structure, and it's not cycling, you know, because remember the double bonds, are the double bonds shorter or longer than the single bonds? Shorter. Yeah. And so, you know, this oxygen's shorter, this one's shorter, that one's shorter, you know, the bond. But, you know, it turns out in carbonate, all the bonds are exactly the same length, you know, when they observe it. And so what people say is the structure of carbonate is actually not an individual resonance form. The structure of carbonate is the hybrid structure. And it turns out that all the bonds are exactly the same. And so the hybrid would be more of a bonus type question on this test. If you can draw out the hybrid for this, you know, that would be extra points. Can you draw out the hybrid for this? Try it. The hybrid is going to be the average of, not 2 like we did last one. This will be an average of 3 structures. So try to draw out the hybrid structure for carbonate.
I didn't know.
What's that?
I didn't know how to draw last time, so I don't know.
No clue?
I don't think anyone visually hybrid. Did you go over hybrid structures? I heard how to draw the name, but I don't remember drawing.
Did I miss hybrid structures? How to draw the hybrid structure? How to draw the hybrid structure is like this. We just average. And so just take a look at the top bond here. It's double, single, single. So what's the average? If it's double, single, single, the average is? Well, is it 1.5? If it's double, single, the average would be 1.5. You know, 2 and 1. But this is 2 plus 1 plus 1 is 4 divided by 3. 4/3 is 1 1/3. And so what we'll do is we'll take that double and divide it amongst all 3. And so the top bond here is what we call 1 1/3 bond. Well, how do we draw 1 1/3 bond? We're just going to use these dots like this. And we're just going to label it a 1 and 1/3 bond. And so, in other words, that double bonds, 1/3 of it goes here, 1/3 of it goes here, and 1/3 of it goes here. And so each of these bonds is what we call 1 1/3 bond. 1 1/3, 1 1/3. And that's just because of how the electron cloud will distribute itself. Bonds, right? And so this shows that all the bonds are the same, except it's more than a single, but less than a double. And so this is how we write more than a single, less than a double, by drawing a solid line and a dotted line. This solid line, dotted line can represent a 1 1/3, it can represent a 1 1/2, and it can represent a 1 2/3. Those are the 3 scenarios that we come up with.
So you don't write it down. You don't write 1 1/3 down next to just the line.
No, we do usually, because by looking at it you can't tell. You know, is that a 1 1/2 or 1 1/3 or 1 2/3? And so that's it. Now, if I look at the lone pairs, this is 2 lone pairs, this is 3 lone pairs, this has 3 lone pairs. This one has 3, 2, 2. So there's 2 ways I do this. The 2 ways I do this is I have a -1 and a -1 with -2. I have a -2 distributed over 2, not 2, but 3 atoms. Or two, I look at the lone pairs. If I look at the lone pairs, I have two always on there. Those are permanent. But the third is only there, the third lone pair is only there 2/3 of the time. 2/3 of the time, that third one's there. And so I got two lone pairs there all the time. And the third is 2/3 of the time. Like that. And so now, what I got to do is I got to figure out the charge. Well, how much charge density is that, as far as the average goes? And so this is all I do. Just like the bonds, I'll do this one. Well, a little different than the bonds. I can do the bonds just the same way. But I'd say there's a -2 charge distributed over 3 oxygens. That means each oxygen will have a -2/3 charge. And so this is going to be a -2/3. This is going to be a -2/3. This is going to be a -2/3. The charge density, just because of how it's distributed out like this. And so if I have a -2/3 times 3, that gives me a -2 charge, which the whole thing is. And so the whole thing carries a -2 charge. Carbon 0 still. So this is -2. And so what this shows is this. The structure shows that all the bonds are equivalent and all the oxygens are equivalent. And in the carbonate ion, all the bonds are equivalent and all the oxygens are equivalent in terms of the negative charge density. And so this is more of the true structure of this. This would be the hybrid structure. I'll put true in quotation marks. I'm putting true in quotation marks because what we're doing is called, quantum mechanics is tough, rigorous. And so there are two approaches to quantum mechanics. There's the quantum mechanics easier or light version, and then there's the quantum mechanics full or hard version.
Would it be okay? Do we have to label every single one of the dotted lines as 1/1/3? Or if we do it once, or could we make a key?
You could just say, that the CO bond is 1/1/3.
Okay.
We call this the bond order in Chem 1A. Actually, we call it the bond order in chemistry. That's the bond order. The bond order: single bonds 1, double bonds 2, triple bonds 3, and then we have partial bond orders. And so, no, you don't have to label each one. I mean, if you're pressed for time, just say, all, CO bonds are 1/1/3. So this is how we draw the hybrid. And so what we typically do is this. When we answer a question, what is the Lewis structure for carbonate? We show the 3 resonance forms like this. And then we might lead it like that. If it's not asking for the hybrid structure, then we don't bother writing hybrid. So the answer for this question would be these 3 structures, or the structures for carbonate. Now, if this would be more of a bonus here, as far as that goes, let me just show you. All right, so if the question were, what are the Lewis structures for bicarbonate, or hydrogen carbonate? This is not complete. What's missing out of this? The charge, the formal charge on oxygen. And so let's go back to this one. I asked for the hybrid, but no one got the hybrid on this one. And so let's revisit this problem again. And let's try to do the hybrid structure for this one. And you tell me the bond order and everything else. Now, there are different ways we draw this bridging oxygen. This bridging oxygen, the way it's drawn here makes it look 180. And so what people try to do is make it look a little more accurate. They try to make it look a little bit more accurate by doing a kink in there. Because the bond angle, the true bond angle, tell me what the true bond angle of this is. The true bond angle here is not 180. The true bond angle is closer to 109.5. Because, you know, there are 4 groups of electrons, 2 lone pairs, 2 bonds. 4 groups of electrons means tetrahedral. Tetrahedral means all the bond angles are 109.5. However, this one's going to be a little bit distorted because of the 2 lone pairs. This one should be closer to what? 105. It's like water. And so a lot of people will draw this bridging oxygen like this. This is more accurate than this. This is 180. Or it looks to be 180. But it doesn't matter how you draw it, because do we care about this structure? When we draw Lewis structures, do we care about it? No. So for example, this OCO angle, this one looks 180. Is that a 180? The OCO? No. What is this OCO angle? You tell me. It's closer to. Tell me just the ideal angle. What would you expect it? No distortions. 120. This is not 180. This is a 120 angle. Now the double bond takes up more space, so it's going to push these out. So maybe it's closer to 122. This one should be like that, 120, but the double bond takes up more space, and this one should be compressed, you know, less than 120. So it's a little different. So anyway, for this, we don't really worry too much about it for the Lewis structure. So we'll go ahead and finish this one. What's missing is the charge. Where does the charge go? The formal charge. Where should the formal charge go? On that. On this. Where does the formal charge go?
For the whole thing?
No. Formal charge is the charge on the individual atoms. The net charge is the charge on the whole thing. So which atom has a charge on it? The bottom one. And the net charge goes outside. We just add up all the formal charges. 0, 0, 0, 0, 9. Okay, what does the resonance structure of this look like? Okay, double bond goes here on the left. No. What would be bad about putting the double bond here? It would screw up the. If I put the double bond here, it would screw up the what? Yeah, it'd screw up the formal charges, right? Right now I only have one, but this puts three bonds in this oxygen, which make it positive. So it's going to screw it up. And so I'm going to put the double bond down here. And so how many total resonance forms are there? Sometimes when I ask, draw all the resonance forms for bicarbonate, you know how many structures I get? A lot. You know why? Because sometimes when I ask for resonance forms, people start moving the hydrogen. See, they put the hydrogen here, and then they'll draw another structure with the hydrogen here, and then another one with the hydrogen here. And so they're moving. And then some people come up with even more structures, because they'll come up here and they'll draw 2 with the hydrogens here. And then they'll move the hydrogen here and draw 2 more. But we never move the atoms, right? Otherwise, we don't know what's a unique structure. If we move the atoms, that's like rotating the molecule or ion in space. We don't do that. So how many resonance forms are there for bicarbonate? Only 2. Can you draw the hybrid for me? You know, so if I asked you to draw the Lewis structures for bicarbonate, I want to see these. And I want to see this double-headed arrow here, indicating that these are, in this case, equivalent resonance phones. Yeah, I'm getting into hybrids because of this, you know, this slide has resonance hybrids. Well, just try to average these two structures out and then tell me what you get. Or, you know, or come up and draw it. Let's see what you guys come up with. If somebody wants to come up and draw theirs, that would be great.